In this lecture, we are dealing with kinetics of electrode process. Here, we are considering the electrode reaction in a kinetic manner, and it's very simple if you are familiar with our previous lectures. Here in this picture, metal on the IHP and metal plus on OHP, and I am representing this as reductant, which is get oxidized, and this can be expressed as oxidant, which is getting reduced. And the same electrode reaction can be expressed in this slide, in this way, which is the oxidant plus an electron giving reductant, and the forward reaction, the rate constant is Kc, rate constant for the cavity process, and the reverse reaction is the rate constant for the anodic process. Here, from the kinetics, you know the equations, rate of cathodic process, rate of forward reaction to cavity process can be written as Kc into concentration of oxidant and Ra equal to Ka into concentration of reductant. Therefore, the potential is equal to, that can be obtained from the Nernst equation, E0 equal to E0 plus Rp by Nf ln Co by Cr. Concentration of oxidant by concentration of reductant, and from this we can have this equation P minus E0 equal to this. Then at equilibrium, we know Rc become equal to Ra, that is Kc into Co equal to Ka into Cr. And if I am taking the logarithm in both sides, we will get this equation, and by converting the equation, we will get a new equation as ln Ka plus 1 by ln Kc equal to ln concentration of oxidant by concentration of reductant, which can be equal to Nf by Rt from the previous equation as ln's concentration of oxidant by reduction equal to E minus E0 into Nf by Rt. Therefore, Nf by Rt into E minus E0 can be written as ln Ka plus 1 by ln Kc. Here we are differentiating this equation with respect to E. First term differentiating second term, and this term we are differentiating, we will get Nf by Rt into E d by d of E equal to 1, and this becomes 0. So we get only Nf by Rt, and we are converting this equation to this type, Rt by Nf d by d of ln Ka plus Rt by Nf d by d of ln Kc equal to 1. Here we are converting this factor as reductive symmetry factor and this term as oxidative symmetry factor. Here 1 by ln Kc denotes that as the forward reaction increases, the potential drops from the equilibrium value, which is cathodic polarization, and this indicates anodic polarization. Then we have this equation, that is from the previous lecture. Rc, we know it's Ic by Nf, and Ra of also Ia by Nf. Then if Ic equal to Ia, we will get the exchange current density, and if there is since we are dealing with over voltage, we will say that Ic not equal to Ia. If Ic is greater than Ia, cathodic polarization is, we are considering I applied equal to NF into KC concentration of oxygen minus Ka into concentration of reductant. We will get the equation after this. Then we are taking the symmetry factor on the caloric side and we are integrating here with the rate constant and here with the equilibrium, as the rate constant is correlated with potential difference. Since E0 is the equilibrium potential, at equilibrium situation the reaction rate constant is the equilibrium rate constant up to the deviation up to the rate constant for evolving that much over voltage. We are integrating up to that much. Then the change in rate constant with the potential change, and we will get this equation from which Kc equal to this much. Similarly, we can have anodic polarization and we will get alpha, the oxidative symmetry factor as 1 minus alpha. Since we are doing total difference, total polarization, we are equally dividing to cathodic and anodic part. So Ka equal to, we will get Ka0 into e raised to nf into 1 minus alpha into A minus E0 by RT. That I said earlier that if you are familiar with the former lectures, you can get easily, you can follow me easily. Hence, the applied over voltage, I applied, we write it as changing cathode current minus anodic current, which is, we can write it as NF into, in place of Kc, we can substitute this value, and in place of Ka, we can substitute this value, and we will get the total equation, the rate equation for the applied current or over voltage. If Kc0 and Ka0, we know it's an equilibrium rate constant. That is the rate constant when the reaction forward and backward processes are in the equilibrium. Since these two equilibrium, the rate constant should be the same, and we can give it as K0. Then the I applied current equation will be like this. Which is known as Butler-Warmer equation, which relates the current, electric potential, and the concentration of reactant and the product, or oxidant or the reductant. This is the short derivation, and you require only this much for Butler-Warmer equation. And if you are familiar or thorough with the previous lectures, you can get an easy idea of this equation. And I stop here with this Butler-Warmer equation, and this much is needed for you as per syllabus. Okay, thank you very much.